Warning, proximity alert.
Digital Antichrist and the patterns of the apocalypse. So, for those who don't already know, a lot of what we take for granted in terms of internet security and data communication is based on a math problem called a trapdoor function. That being the use of prime number multiplication um, resulting in is what is known as a semi-prime. So for example, take two prime numbers, just 3 and 7 for example. Multiply those together, you get 21. 21 is a semi-prime, and there is no currently known accepted algorithm that will reverse that value back into its two factors. And it's important to note that semi-primes always consist of two and only two prime number factors. I mean, other than itself and one, but so that's important to note. Nobody, at least not published or widely known, has a truly testable function to factor a semi-prime. There was so back in early 91, there was this monetary math challenge put forth to, in my opinion, was really to test the public, or the test of public's computing power, what they had available to them. So just Google RSA factoring challenge and read up on it. They stopped that in 2007, probably because it became maybe a liability. That's just the way I look at it. So the scary part here is that once quantum computers are developed to a useful extent, RSA will be broken, dead. Our last known effective encryption trapdoors, what they call ECC, which is elliptic curve cryptography. You can Google that as well. Essentially, it's being adopted today, and I would consider it our sort of fallback plan. Internet chaos. Okay, sort of. It's to me, it's more of when will this happen? Yeah, that's right. When. I don't consider the if anymore. I think people are already working on this problem, and I wouldn't be surprised if the solution already exists. So the persons, or group, perhaps they'll try to use it for good, but only evil will ensue. So actually, that kind of sounds familiar. Use it for good, and Lord of the Rings. Anyways, essentially, the internet will be mostly broken, as will many of the sort of IoT type systems, Internet of Things. I believe a lot of them still employ the RSA stuff. Anyways, ECC will most definitely be our last hope. Patterns of the apocalypse, spreadsheets, the digital angels of death. Okay, for this example, I need to create a table, more like a game board. Let's just think of it as a game board. And what I'll try to do is solve a problem. Now, you've most likely seen a spreadsheet similar to this. I use this often when I'm just going through some number discovery stuff, because it produces some really cool patterns. So really what this is it's a multiplication table. 9 times 9 is 81, for example. And what you're going to find down, diagonally down, are all of the square numbers. So numbers multiply them by themselves. Easy to find a square root for these, which is why they're never going to be used as an RSA key. So we'll just mark those by green. Now if you look at this as a game board, the only thing that you're going to really know about the game board are these square numbers. you really don't know where the other numbers are actually sitting. I mean, I'm showing them here, but just for illustration here. So let's just take some of these primes. The reason I'm using primes is because they're harder to find a pattern for. You don't have to use these, but I'm just marking them off in case I want to use them when I'm explaining something. Okay, so let's just say the game is, pick a number, random number. I'm going to use a semi-prime. You can use any number, doesn't matter. But I'm going to use a semi-prime, 187 in this case. Now, if you didn't know what was on this game board or this multiplication table, and I said, where's 187? You wouldn't really know. The only thing you would know about the map or the board is all the squares that run diagonally down. Okay? The other thing that's either obvious to some or important to note is that this diagonal is really just a crease in a mirror. So on this side of the game board is identical to this side. So 23 is 23 here, 44 is here, 30 is here. It's just a mirror image of what's on the other side. So you can use this side and ignore this side, but for some of the interesting patterns I'm going to show you, I need both sides. So just to illustrate, yeah, that you couldn't really tell where 187 was. You would have to go through sort of a brute force type of factorization, which is you take 187 and you divide it by 1, then 2, then 3, then 4, until eventually you get to either 11, and you'll have an even number telling you that, yeah, that's one factor. That is the main problem. That is the trapdoor function problem. So some of the patterns I believe that may be useful when trying to determine where or how to solve the trapdoor function. Something here, I'll just show you. So let's just take this number 91, and I'll mark it off so we know what we're talking about, and then I'm going to draw a block around it so you also know the numbers I'm referring to. So the sum of these numbers down here in the bottom right hand corner is 819. 819 divided by x is 91, and that x is really 123 times 123, which is 9. So 819 divided by 9 is 91, and I'll just prove it here. I'll prove it to you. So 9 times 91 is 819, which is sum of all these numbers. Now this works anywhere on this map or this grid, which is important to know, because it may be relevant to determining an algorithm that can determine where you are on this board or map or this grid. You can take that and basically do it anywhere, as long as I'll try it with even numbers. I don't know what the result is with even numbers. We'll just try here and see what happens. So here's an even square. I don't really care about even squares, to tell you the truth, because I'm not really looking for anything other than semi-prime factorization. So this is it's 1100 divided by 16, right? So 1100 divide that by 16, and we get some odd number here. 68.75, which is probably closest to being here in the middle of all this group of numbers. But let's not go there. Not interested in that right now. It's not a pattern that I've looked at much. I'm really interested in the odds, because odds are what are going to give you the factorization of some prime number or semi-prime number. So we can take 3 by, say, 1, 2, 3, 4, 5. I want to mark this off. reference. So 1, 2, 3, 1, 2, 3, 4, 5. That's 15. The total is 780. So let's take 780 and let's divide that by 15. We should get 52. Yes, we do. So I guess you can try this. It's a cool pattern. Just you take the sum of the number divided by the actual number of values that came up with the number, and right in the middle is your answer. Cool, very cool pattern in this grid. So that is part of pattern A. Now, I've worked on a different spreadsheet here, but it's really the same thing. I have a grid, and I marked off the squares, and I also have this working pattern down here, which is cool. I wanted to show you. This is part 2 of pattern A. There's a part 3 to it. I really haven't had a chance to sort of get it ready, and I may do a follow-up on it to show you something else to do with this pattern, sort of another way to actually calculate it. Let's just, I want to show you this first. So these numbers, 247, I just repeated them right across. I wanted to show you a cool pattern with that. So it's really this pattern here. I'm copying and I pasted that down here. And it works like this. So here's the pattern, the ones and the zeros. The ones being the numbers that I wish to use in the calculation. So for 1 and 1 refers to these two numbers. I copied them down here. And when I sum these up, I get 494. If I divide 494 by 247, I get 2. If I rotate that pattern from this to this, I get the same answer. And of course, we're now with 3 across, 741. Divide that by 247, you get 3. You take that pattern, you stand it up, you actually rotate it. That's really all it's doing. And again, when we get to 4, here's the next pattern. There's 4 each corner. Add those up. 988 divided by the center value, you get 9. If you get 4, rotate that pattern again, and you get 988, 4. Cool stuff so far. Then we're up to the 5 different numbers. Okay, this time we're using kind of a cross pattern, and then we take that, rotate it, and of course the same thing happens. Next pattern's 2 verticals. Rotate those, 2 horizontals, they become 6. And then we have the I, H, until we get near the end where we have 8 numbers. Of course, if you rotate this, you're going to have the same pattern. And of course, you can't really rotate that because you get the same pattern. But I've just kept 9, 9, 8, 8 just to keep the pattern. You know, you can rotate them theoretically, but they end up with the same value in the sum. So that is part 2 of pattern A. Something else to note, just sort of cool to mention, is that there is another pattern here you could potentially use to deduce where you are on the map, is by taking this game board map grid and across the entire thing do a modulus of 3 on it, and you end up with 9 patterns. Okay, and 9 patterns really consist of this one pattern, which is 120, 201, and 000. If it's shifted at all, it ends up being, if you shift it to the left, they wrap around. But this pattern exists. So this one, no matter where it exists on the on the 9 different possible locations, it maintains this pattern. So if we have the 1 and 2, so let's put the 1 in the middle. here, for example, the ones in the middle, that's 1, 2, 2, 1, and here's the zeros. Everything just wraps around. So one other thing you could do is in the 247, if you take sort of 247 by 3, you end up with 1. Now it's only one of two possible places. It's either going to be a pattern that looks like this, where you have a 1 and a 2 and a 2 and a 1, or it's going to be this. So it's either going to be this or this is really where your 247 sits on in the bigger repeatable pattern grid here with the mods. So that's another option you can use to determine where you are on the game board. I like to call it a game board because to me it's a game. To others it's just a grid. So yeah, that's cool. Interesting stuff. The next pattern is, and I'm going to probably pause it here while I get it ready, because I have to think about it again. But it's about summation. So let's just go all the way up to really high numbers. Now I don't know if I got this right, but I believe it is this times this plus 1 divided by 2, 55. Yes, I think I got it right the first time. I just learned this kind of thing today. I had a different algorithm to use to actually come up with that using squares, but this algorithm has less steps. So what's cool about this is, let's just take, like I said, I might have to go up a lot higher. Let's go way up, say 1, good enough. And then we'll take this, of course, and we'll bounce all the way up to here. Okay, let's take two semi-primes. Let's take 11, 17, or 11, 13, and we multiply that by 13. We get 143. We go up to 143, which is here. We get this number, 10,296. Okay, so I take this value, which is the 143, and I do a division on that. And I got 72. Now what's really cool about the 72 is if I do this, and I keep adding 72 all the way up, okay? And I take that answer, which is the larger value that I came up with, and I divide it by these 72s. That is the gap, I guess you want to call it. The gap that leads to factorizations. 72. Eventually, it's a lot quicker than trying to go, 143 divided by 1, 2, 3, 4, 5, 6, all the way up brute force. This is somewhat of a brute force, but it's like a algorithmic sieve, because I have a value I get out of an equation. It's not a preset set of numbers. 72, why that ends up working and it always lands on these factors, don't know. Seems to work for everything, and it's likely going to be a very fast way to get to the factors you're looking for. But that is pattern B. So I hope you found this interesting. I am going to provide this spreadsheet to anyone who is interested. I'm still working on it. I kind of want to make it a little more presentable. Maybe I'll I'll write an application or an app for it to help determine how much quicker it is to find factors using this pattern than it is through a brute force type application. Hope you found that useful and interesting. Okay, some final comments. First of all, I wanted to say that this is probably as close to clickbait as you'll get from me. However, the purpose of the video was to show some patterns associated with the multiplication table and how finding the placement of a number could be deduced and potentially calculated. So I guess, why is it important? I guess the point is, if you can locate the spot on the table, then you can also find the factors of any number, thus breaking the trapdoor problem and blowing a huge hole into internet security. That person, people, the organization that find or have found a solution hold a lot of power. They can potentially infiltrate, circumvent security, steal information, your money, your life, and do the same with countless other people. I guess I'm suggesting that working together on the problem introduces and raises the threat level so that RSA can be decommissioned and something like ECC can take its place entirely. Math to me is all about patterns, and in that example I was showing, I was able to show a repeatable pattern, meaning the underlying algorithm can be found and it can give you answers, to where to locate it on that map. Essentially, it's if you can create that algorithm, the underlying algorithm, to repeat that pattern for the number, then you can find the factor. So it's just a matter of time before that happens. Anyways, thanks for watching. Like, share, subscribe. Thanks.